hit the record button, so we are now live. And I have my glass of water so that I don't cough and suffocate while talking. So yeah, last time we read like the first two parts on distributions and how to define them, and we saw that we could like extend the derivative operator to it, and it was pretty nice, especially for like finding solutions to partial differential equations and differential equations where maybe the initial point is not necessarily, or the initial condition is not necessarily differentiable or smooth. And this next, and okay, it was nice because from a fairly simple construction, we got some pretty nice results. And today we'll continue in that part and go a bit beyond. So the first part was about weak solutions. So remember that if you have a partial differential equation, usually people look for a classical solution, so a solution that's differentiable and that satisfies the equation. But if your initial condition is not does not satisfy these conditions, then okay, you can still get something in terms of distribution. So if you have a distribution that satisfies this equation in the distributional sense of the derivative, then we call that a weak solution. So for example, the function u of xt equal ht, the Heaviside function, times ex exponential of x, is a weak solution of du dx or is equal to u. I mean, it's a bit trivial one because you could remove the Heaviside function, it would still be a solution, so not super interesting, but we can go through the calculation through that indeed, if we, after we do find that d over dx minus the identity operator applied to u is the equals 0, so that's all right. And yeah, there's a couple more examples of equations where we find some solutions. So for example, they give the transport equation, which is a reasonably classical equation in PDE, where it's basically it's typical to put all of it in one side so that equation equals 0, but really it says that the derivative with respect to time of my function u is simply some constant c times the spatial derivative. And usually we need some initial condition u of x at sign times 0 is equal to f of x, where f is some at least differentiable function. And okay, and sort of in the classical sense, it's easy to see that okay, if I have one solution is to simply take u of xt equals f of x plus ct. So you can imagine that your function is just moving along in some direction, so you're just shifting it. And yeah, so this is it's a solution that you can trivially check, and actually it still works if f is so it's not c1, but it's in the locally integrable function, and those define distributions. So if we again we do the manual work of okay checking that it works, and okay to actually go beyond that, there is the proof in the book does a change of variable psi where we replace so we take the x plus ct and replace by some psi, and eta we take the t and replace by eta, and okay we have some change of variable formula where we have the determinant of the Jacobian that appears, but in this case it's just 1. But yeah, eventually we get that this integral is equal to 0. So we have a distributional derivative of the transport equation, or a distributional solution. And okay, I won't spend too much time on this one, but you can do exactly the same for the wave equation, where so the wave equation is essentially the same thing, but with second derivatives. And a classical solution is f of x plus t plus f of x minus t. So you have two waves traveling in both directions, and okay, it still works in the distributional sense. I won't go over the proof, but it's pretty straightforward. But one of the tricks is to use the fact that the derivative operator commute. So essentially we can treat these differential operators as kind of polynomials or polynomials expression, and so we can move them around a bit. So okay, that was with weak solutions. The second part was about, okay, we have a vector space of distribution. It's nice, but maybe we'd like to have some more structure. Maybe we'd like to be able to take the product between two distributions. Unfortunately, we cannot take the pointwise product of two distributions in general. So to comment a bit on that, when you have a vector space where we can take a product of two vectors to produce another vectors, for example, the pointwise product, we call that an algebra, and algebras are pretty nice to have. For example, they also appear in solution to classical ODEs. Unfortunately, we cannot take the pointwise product of two distributions to get a distribution in general. And for example, we have this function f of, so the 1 over the square root of x, which is locally integral, so it defines a distribution, but f squared is 1 over x, and this is not locally integrable, so it does not define a, we cannot get a distribution with this. So, okay, we cannot quite define a product between distributions, but we can at least define taking the product with a distribution with some smooth function. So if I have some smooth function alpha that's infinitely differentiable, then I can define the product of alpha t, where t is a distribution, as simply, again, as with all things in distributions, we define operators in the dual sense. So we just move alpha to the other side. Because alpha is smooth and phi is a test function, alpha phi is also a test function. And it's easy to show that, okay, this operator as defined is linear and it's continuous. You basically have to use the multivariate Leibniz rule. So I give it on the bottom, but it's mostly a lot of it works as you would expect. It's just that these ends here are like multi-indices, so it's the general sense, but it's not worth going over. One nice property is that almost trivially that okay, if I have some f that's a locally integrable function and I take the product with some function smooth function alpha, then the alpha tf is simply t of alpha f. So nothing too fancy. But this product has some nice properties. First of all, okay, it's linear, no problem. Like even though it's not a proper product on the distributions. Hi to the people who just joined. I see one of them already left. So we have some fairly straightforward properties that, okay, if we multiply with the function that's constant 1, we still get the same function. It also plays nice with the derivative. So the derivative of the product of our alpha times t is the, okay, classical, in this case, derivative of alpha times t, which is distribution, times plus alpha times the derivative of t. And sort of as a, maybe not quite a corollary, but if we take then the product of some alpha times the Dirac function at some a, then it's just alpha evaluated at a times delta a. No big surprises. But these properties, when you put them together, it tells you that the set of distributions is actually what's called a C infinity module. So a module is just a vector space, but where instead of a field so remember that a vector space, you have a field that that you can scale vectors with. Here in this case, we have the set that we are scaling with is not a field, because we do not necessarily always have an inverse for every alpha. So it's a ring instead. And so when we have a vector, like almost like a vector space, but with a ring instead of a field, we call that a module. So it's for a neat thing to notice that okay, we have some weird algebraic structure because we have a vector space, or almost a vector space, with some ring of functions instead of a instead of a like a scalar field. And okay, so to give an example from quantum mechanics, so we had seen previously the position operator that takes a function from so the square integral function and gives it another one. It typically takes some f and multiplies by x. And we had seen that this operator has no eigenvalue, so we have no eigenfunction that's such that q applied to this eigenfunction is lambda that's down the eigenfunction. But if we extend this to distributions, which we can, then we get that the Dirac deltas then act as eigen distributions, one might say, of the operator, because q applied to the Dirac operator delta A is simply x times delta A is equal to A times delta A, so it works out. So it's nice that when expanding our space, we actually get some more we get some different spectral structure, although in this case it's a bit annoying because we literally have uncountably many eigenfunctions. Oh, wow, I see a lot more people for the functional analysis reading group. I think some of you might not be knowing what you're getting into, but we'll see if people leave. Okay, so moving on to the last, and the final section of the book, actually, which is about taking Fourier transforms of distributions. So just like we defined extended differentiation for Fourier transforms, we'd like to also define and extend Fourier transforms. And so ideally, we'd like to be able to take like hat, so t hat of some integral function f phi, and basically have it be equal to t of the Fourier transform of f. But the problem if this is that we could like go along with the calculation, but the problem is that if we take a test function phi, its Fourier transform may not have compact support. So taking the Fourier transform of a test function does not give you a test function in return. So this definition, as we've done it above, is not quite legal in at least in the space of test functions. I see no people left, so interesting. So to actually define extend the Fourier transform in something that looks at distribution, we actually have to consider a larger space of functions. So we take what's called the Schwartz space. Actually, it's not larger; it's smaller. So we define the Schwartz space of functions as the set of test functions, such that they're all smooth and they're test functions, and they satisfy that for all L and M, so integers, the supremum norm or the supremum of x of the L times the mth derivative of phi has to be finite. So it might be a bit harder to view, but it's sort of a very restrictive condition on these test functions. It's still a vector space, and it's still closed under differentiation because we still allow to take derivatives, and because we also have some bounded test condition with respect to products by powers of x by doing linear combinations and scalars. That means you also have something that's closed by multiplications of other polynomials. So actually, maybe I think this is wrong on the top and the correct thing is on the bottom. So the space of distributions is part of the Schwartz space. But one example of a function that is in the Schwartz space but not in the distribution is e to the minus x squared. So e to the minus x squared, it satisfies these two conditions above, but it does not have a compact support. So it's not a it's not a test function, but it's still in the Schwartz space. So once again, we have to define what it means to converge because it's not quite a metric space. So we say that some sequence of Schwartz functions converge to 0, so the function has 0 everywhere, in the Schwartz sense, if for any L and M above 0, the supremum norm of x to the power of L multiplied by the phi n, and we take the f derivative, that goes to 0. So it's, again, a little more less intuitive definition. But we have some nice properties out of that. In that, in this space of Schwartz functions, taking the Fourier transform is so first of all we get a Schwartz function, and it's a linear and continuous map. So it's sort of a more appropriate space to do to talk about the Fourier transform. Yeah, so basically the two things I have on bottom are essentially what I just said. And okay, now we can talk about distributions, but so remember that we define distributions at essentially the dual space of the test functions. In this case, we'll define what's called tempered distributions as the dual space of our Schwartz space. So it's the set of continuous linear forms on the Schwartz space, so functions that go from the Schwartz space on say R and to the complex number that satisfy that it's linear. Whoops, I managed to throw my stylus across the room, sorry. So they are continuous in the Schwartz topology. So it's a space of tempered distributions, and since the space of distributions is a subset of the space of the Schwartz space, we have that the space of tempered distributions is included in the space of distribution, but note that it's because we're taking the dual space, it has to be the other way around. So you might expect that because the space of test functions is in the Schwartz space, that then the space of distributions should be in the space of tempered distribution, but it's the other way around. So for example, an example of a function that is in the Schwartz space but not in the that is in the distribution but not in the tempered distribution is e to the x squared. And for example, we could take t e to the x squared times our function e to the minus x squared, which is, remember, a Schwartz function. And integrating this, we get essentially 1 over the real line, and so that's not finite, and so that doesn't work.
We've only mentioned one-dimensional spaces of real numbers so far.
Yeah.
Similar construction works for multiple dimensions?
Yeah, I think like the book does a bit quickly over it, but I suppose that it does work in general. Like we could do the more general definition, but for intuition's sake, I think it's easier to just think of the one-dimensional case.
Yep.
Okay, so basically the rest of the section is about examples of functions that are in the tempered distribution. So integral functions are in are tempered distributions, and we can see that if we have some function such that the integral of the absolute value of x, sorry, again the pollen is killing me. So we have a function f such that the integral over the entire real line, Jesus Christ, of the absolute value of f is finite. Then the associated distribution is a tempered distribution. So just take some Schwartz function phi, and we see that we expand the inner product or pseudo inner product and get that it looks like it's bounded by the norm of f, which is finite, times the absolute norm of phi, which is also finite because it's so remember it is a distribution. And so that means that if we take some sequence of phi n that converge in the Schwartz sense to 0, then this inner product also has to go to 0. So we have that TF is also a tempered distribution. Another example, the Dirac delta function is also a Schwartz function. To see that, okay, it's easy to show that just evaluating the function at 0 gives us is linear, and that if we converge to 0 in the Schwartz sense, then of course phi n of 0 has to go to 0, and so no problem with there. And okay, we still have we can still extend the derivatives to tempered distributions exactly the same way we did for distribution, which is we define the derivative of t as simply in the inner product sense as minus the t times the derivative of phi. So nothing special. Some other properties that, okay, I mentioned that we can multiply by polynomials. So for distribution, we could multiply by smooth functions. Unfortunately, we cannot do that anymore for tempered distributions. For example, remember that the constant function 1 is a tempered distribution, but if we multiply it by e to the x squared, which is a smooth function, we get x squared, which is, as we had shown previously, not a tempered distribution. So we cannot multiply by a smooth function, but we can still multiply by polynomials. So you can imagine, if you think about the smooth functions as Taylor series, that means, okay, we can take truncated Taylor series or finite polynomials that works, but infinite ones not anymore. So this all works because we've almost by definition, so taking some t, so some tempered distribution, we can always multiply it by t. And by the fact that, okay, we can compose, we can linearize and sort of do linear combinations, and by the definition of what it meant to be a Schwartz function, this still works, and so we have a well-defined distribution, tempered distribution in this case. So,
is this the most permissive multiplication that you get, just polynomials?
I'm not entirely certain. There might be like some like you might find some class of like smooth function that you can multiply and still get things to work. I think probably if you have a smooth function that is bounded, that should still work.
Sure.
And probably like remember that like L1 is in the space, so like polynomials work, but you can probably find some other classes of maybe smooth function. And I think there's like an exercise about showing that any bounded function is also also a tempered distribution. So mostly that should work. But one interesting thing that in this space of distribution, we can get some unbounded functions. So remember that for most of our Banach space and Hilbert spaces, we had functions that had to converge, that had to be bounded. And in this case, we get some functions that don't, which is interesting because we just changed the topology a bit. So we're reaching the final part about Fourier transforms. So remember that this is what we wanted to do from the beginning. So it's almost trivial to show that, okay, we can just define the Fourier transform. And in this case, because we know that the Fourier transform of a Schwartz function is still a Schwartz function, we can just define never mind. So we can just define the Fourier transform of our tempered distribution as simply t times the t applied to the Fourier transform of its input. And for okay, there's an exercise about showing this is true, but with all the things that we've seen, it's trivial that that is true. And for example, if we take the Fourier transform of the Dirac operator, remember that the Dirac operator is like just a single point that we're picking out. Well, just apply it and okay, just evaluating the Fourier transform at 0, and okay, we do a bit of math, or at least just plug in 0 in the definition of the Fourier transform, and we just say, okay, we'll just taking the integral of phi over the real line, and so it's basically just applying the distribution obtained from the temporal distribution obtained from just the constant function 1. And so we have that the Fourier transform of the Dirac delta is simply the constant, the function that is 1 everywhere. So interesting that it sort of makes sense if you remember that Fourier transform, they sort of, if you have some very localized function, the Fourier transform will be very spread out. And so this is almost the
principle, yeah.
Like the most the best example of this, because you have the function that's not the function but the distribution that's super localized, it's just 1 point, and here is just spread it over the whole real line. Yeah, so they give a couple more properties, but they don't prove it. So I assume they didn't want to prove them because it was a bit technical. I think they mentioned a couple of proofs that like they could be done, but were a bit tedious. But we still have the property of that the Fourier transform of the derivative of t is 2 pi I sigma, here sigma being a variable, times the Fourier transform of t. And we still have almost the nice property of the convolution. So we can take the convolution of two tempered distribution to get another tempered distribution. And we still like, okay, that taking the Fourier transform of the convolution is simply the pointwise product of the Fourier transforms. In this case, it does not. It's a bit weaker because, okay, we can take one of them being a temporal distribution, but the other one has to be a compactly supported normal distribution for this to work. And they do not give the proof for that, but I assume it's related to the fact that we can multiply by polynomials and such. So yeah, the last thing about in the book is about fundamental solutions, also known as green functions. And the idea is that if we have some, say, partial differential operator with constant coefficient, so d, which is our operator, being just a sum of ak times dk. Note that here these little k's are multi-indices, so these might be just like product of my operator of like dx times dy times dz or times dw squared. So in this case, we're in the d-dimensional case immediately. And we define a fundamental solution of this operator as a distribution E, or tempered distribution E, that satisfies dE is equal to the Dirac delta. So these are much more well known as green functions, and the reason these are really nice is that if we know the green function of an operator, we can solve any inhomogeneous equation. So du equals to g. So g is just an arbitrary function, or maybe we have a couple of constraints on it, but generally we're a bit free. And you can find the solution u by simply taking the convolution of g with our fundamental solution. And under some condition this works, so we can just apply it and see that we get indeed the solution g that we wanted. Note that there's a fair bit of hand waving involved here because the book also does. An example is that if you have in a previous exercise we had that the absolute value of x divided by 2 is a fundamental solution for the second derivative. But a maybe more interesting example is for so I think not necessarily the second derivative, but might be one case. If you have the Laplacian, so the sum of second derivatives across all your dimensions, and you look at the fundamental solution to that, you get a Gaussian. And this is related to, for example, to diffusion models, because in diffusion models you're adding this noise, which is almost like applying the Laplacian operator. And as you progress in time, you converge to a steady state that is looks like a Gaussian, it's because the fundamental solution of the Laplacian operator is a Gaussian, or if you're some non-Euclidean space, maybe something else, but generally it's something like a Gaussian, so just like almost a bell curve that spreads out.
And the other one that everyone knows is Coulomb's law.
Yeah, except I don't, because I haven't done much physics when I was studying. So
yeah, it basically says that the potential from a point particle goes like 1 over r.
Right.
So it's the Green's function for Maxwell's equations, or well, for the Maxwell's equations without any current.
It happens to be the same as the gravitational function.
Indeed, it does.
Yeah. So yeah, but Green's functions are like the one of the nicest part in PDE is that okay, I just have to solve this, find this one solution, and then any other problem, or almost any other problem, I can just solve by taking a convolution. So it's in a sense, you can think of it as decomposing G, like when you're taking the convolution of G with the drag delta, you're like decomposing G as just a sum of drag deltas, and then applying the solution operator to all of these drag deltas. So it's sort of the idea. Okay, I think that's all my notes for today. So if you have anything to discuss, let's do it. Wow, 2 people immediately left.
Ouch.
I mean, honestly, it's nice to have some attendance for once, because
usually I'm the only one here besides genetics.
Yeah, you can tell this reading group has maybe going on for a bit too long, so at least we finally reached the end.
We finished the entire textbook.
Yeah. Yay. Like I almost managed to do all of the exercises, although some of the later ones I was like, okay, I'm not sure what's the trick and I don't have time, so I'll just look it up. But yeah, I don't know if someone has questions or would like to discuss something else, or no?
Nope, nothing from me today.
Yeah, I guess. I mean, if you haven't done the exercise like this, not a lot of them, but they're fairly short, although some of them are a bit more tedious, but like, yeah, as far as I'm concerned, I'm happy with what I learned in this last chapter, so. Yeah, if we have nothing else to discuss, then we can call it a day. As mentioned in the last message I sent, the last ping I sent on the reading group thread, is that okay? We're done with the book, so we'll no longer be meeting about the book. But I think it's not quite the end for this reading group. In particular, I've been wanting to, both for myself, but I think it might be interesting to a couple of people, to talk about the dual tangent kernel stuff, which directly applies some functional analysis. And maybe if I think I have to see how much time I need to read up on NTK, but if I see some other stuff, or if people want to see some other stuff in machine learning that's related to functionalities, we can talk about it. But otherwise, yeah, I think it's almost the final sessions for this reading group. So congratulations.
I would be interested in turning this into like a general math for ML discussion group.
Yeah, that might be. Yeah, that might be an idea actually.
Maybe have some other people presenting stuff as well.
Yeah, that might be nice too, but it's hard to do. Like I don't know how Tanishq managed to get people to sign up for presenting, because I haven't had such luck. But yeah, it might be an idea to just expand to just math for ML and maybe less present, but we'll see. I think there was some people trying to start a geometric deep learning group actually over in research.
That would be
Although
interesting. Yeah, I've looked over the video lectures for that on YouTube a little bit.
yeah, that's the thing. Like if you had the video lectures, there's less of a point of doing a reading group.
Geometric, geometric learning, like how, like in like the geometric algebra stuff, or
No. So like it's a bunch of people. Like it started from the people noticing convolutions are nice because you have translation invariant, and so it was this whole thing of designing networks, network architecture that respect some symmetries of your input. So say you want an image network that's invariant up to rotations, or that satisfies some more complicated symmetries. For example, like graph learning also falls into that category. So it's more of a general. I have like these symmetry relations on my inputs that I want my network to respect, and so how do I design my network architecture to do that? But so it's nice because it's a more mathy approach to ML, and they've had some interesting successes for that.
okay.
And I think it's like the same people. Sorry.
Yeah, I was saying that essentially in geometry learning, we have to avoid trying to converting it into some other space and keep it in the native space.
Nice. Correct me if I'm wrong. I think almost the same people that were into geometric deep learning, they also were proponents of the like category theory for machine learning, but I might be confusing. So yeah, like there's like a whole branch of just more bring more math into machine learning, and they've been doing their own thing, but it's some nice stuff.
Yeah, the geometric one sounds like it might actually be useful in practice.
Yeah, I know. Like even on here on EII, there was a channel on equivariant learning. So like I know people have worked on this, but
There's also the group doing the Minerva replication, so kind of the other direction.
Isn't Minerva like it's a text model, right? Or
Yes, so in this case it's ML for math rather than math for
Oh, right. Yes. Yeah, in that case, I'm not sure if it's really geometric deep learning in this case, but it's the other way around.
No, it's totally off topic from geometric deep learning, but in the general thread of math and deep learning, something we could potentially, draw an interest in.
We'll see. Anyway, I think I'll call it today, also because I have to wake up earlier tomorrow, and I'm not super happy about it. My students tricked me, so yeah, I think we can call it a day. Thanks for the people who attended. I hope this was a non-zero amount of enjoyment. So